All right, so this is the video for the Unit 1 review for Algebra 1. So starting off, the graph shows the relationship between the time and distance from home. So we want to know what are the independent and dependent variables. Our independent variable is always our x-axis, and our dependent variable is always the y-axis. So in this case, our independent is time, and our dependent variable is distance from home. Okay, so then we want to know, what does this section from 12 to 1 represent? So 12 to 1 would be this section right here. So in that section, because it is going up, we are increasing that distance from home, so we are going away from the house. We're going away from home. So then the section from 1 to 3 is, let's see, 1, 2, 3. So that is this section, which is right up here. So if you notice with that one, my distance from home is not increasing, it's not decreasing, it's just stayed the same. So we are stopped somewhere, which we might have gone to a friend's house, we might have, I don't know, gone to see a movie or something, who knows. And then the section from 5 to 6 is this section right here, and that is when you are heading back home. And then eventually you are home. Okay, so for the next one, a car's speed increases as it merges onto a highway. So I'm actually going to number these as I go to make my life a little bit simpler. So a car's speed increases as it merges onto a highway. It travels at 65 miles per hour on the highway until it slows to an exit. So it travels for a little bit, and then it slows to an exit. Then the car stops at one traffic light before reaching its destination. So reaching the destination would be 5. And we want to sketch a graph of the car's speed over time. So because the car's speed is going to depend on what time we're looking at, that means that time is our independent variable, which it pretty much always is, and then speed is our dependent variable. So then to draw this graph, first little segment is that it's merging onto the highway. And it kind of depends on how you see it, because maybe you think that they're stopped at a stoplight. If you think they're stopped at a stoplight and now they're running onto the highway, then you may have a graph that looks like this, because you were stopped and now you're going fast. So that is section 1. So then when the car is traveling 65 miles an hour, it has to travel before it can get to that exit. So I'm just going to be keeping that speed the same. Then I have to slow down because I'm going to exit. 3, there it is. Then, as I'm slowing down to this exit, now I have to actually stop, which actually, you know what? Probably don't stop quite that quickly. Maybe we just keep this going. Kept it consistent. So down here, we are stopped at the stoplight. So then we are stopped at the stoplight, and then we have to go reach our destination. So we may come back up, maintain, and then we reach our destination. Okay. And keep in mind, your graph may look slightly different, but as long as you can justify what is happening on the graph with what is happening in the story, then it's fine. I've seen this graph many different ways. So, and we did need 5 sections, right? Oh, it didn't say. Okay, so now we have a professional surfer paddling out past breaking waves, riding a wave, paddling back out past the breaking waves, riding another wave, and paddling back to the beach. We want to sketch a graph to represent the surfer's possible distance from the beach over time. So again, we have that time. That is always going to be your x-axis, because your distance from the beach is going to depend on what time of day it is. It may not be that it's, 5 minutes in, I have to be out there. It just means that you can't change the time. So distance from beach. So I'm going to number this one like I did. He paddles out past the breaking waves, rides a wave, paddles back out past the breaking waves, rides another wave, and paddles back to the beach. So sketching this graph, I'm going to be at the beach, then I'm going to paddle out past those waves. Okay? And then when I ride the wave, I'm going to come back towards the beach a little bit, but then I ride the wave and I paddle back out. And maybe this time I go even farther out. Then I ride the wave, which brings me back in, and then I start paddling in. And it may even be that I paddle really slowly. So actually, I'll change this a little bit. I'll make this fast in and then slow paddle back in. So we paddled out, rode a wave, paddled back out, rode a wave, and paddled back into the beach. And I have that less steep because the chances are I'm paddling in slower than the wave would have brought me. Okay? So then for 4 and 5, we need to represent the relationship using words, an equation, and a graph. So if we start with Jaden's blog, the number of months would be our x-axis. And then the number of subscribers would be our y-axis. Because much like my YouTube channel, the number of subscribers is going to depend on the number of months I've had it. So now looking at the number of months, I'm going to actually label this 1, 2, 3, 4, 5, 6. We don't even go that high. And then I have to go from 40 to 80. And looking at the lines, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8, so I'm going to count by tens. 10, 20, 30, 40, 50, 60, 70, 80. So then you're just going to plot the points. At 0, he had 48 subscribers. So he had some people subscribe to him before he started keeping track. Then after 1 month, he has 56. Then at 2 months, he has 64. 3 months, he has 72. And 4 months, he has 80. So you notice for the most part, this does appear to be a linear graph. Now, with this graph, it is going to be a discrete graph because although we may be able to actually look at partial number of months, I can't have partial number of subscribers. So because I can't have partial number of subscribers, I can't combine them. So then to represent this with words, you can say Jaden increases by, this is plus 8, plus 8, plus 8, plus 8. So he increases by 8 subscribers per month. And you can even mention started at 48 subscribers. Okay, so then to come up with an equation, if we use something like slope-intercept form, we have to know where I started at. So 48 would be my B. And then the M is my rate of change, which we know is 8. Okay. And I'm just going to box this so it's a little bit more explicit. Okay, there we go. All right. So then for 5, we're going to do the same thing. We have number of tricks, number of biscuits. So number of tricks is going to be our x-axis, and the number of biscuits is going to be our y-axis because the number of biscuits given is going to depend on the number of tricks done. And looking, let's see, we have 20. I have 8 lines, so let's count by 5s, maybe. Sure. 5, 10, 15, 20. We don't have to use the whole graph. It's okay. But if I graph this, when I do one trick, when my dog does one trick, I still have 20 treats. When he does 2 tricks, I have 17 treats. When he does 3 tricks, I only have 14 treats. And then after 4 tricks, I have 11 treats. So looking at this pattern real quick, that's -3. This one's -3. This one's -3. And much like the one before, we have a constant rate of change, but given what we have, this graph is also going to be discrete because I can't do half a trick, and I could give half a biscuit, I guess, technically, but my dog can't do half of a trick. So then, to explain with words, each trick uses 3 treats. And you can even say starting with, let's see, if I went up 3, that'd be 23, right? So starting with 23 treats, each trick uses 3 treats, or biscuits. If you want to be really specific, say biscuits. Okay? So then, if I want to do an equation, I look back at what I have. Starting with 23 treats, that's my y-intercept. Each trick uses 3 treats. Because it's using the treats, it's going to be a negative 3. Okay? Oopsie. X plus. All right, there we go. All right. And that would be our equation. So then for 6 and 7, we want to decide what a reasonable domain would be, if the graph would be continuous or discrete, and actually graphing it. So for A, actually, I'll do lowercase, why not? So for part A, a reasonable domain, if we are buying, your cost C to buy W pounds of walnuts is $6 a pound, represented by C equals 6W. Looking at pounds of walnuts, the only numbers that make sense with this is that they have to be bigger than 0. So my domain would be x values greater than or equal to 0. So then for B, we have to decide if the graph will be continuous or discrete. Because we're buying walnuts, it's going to kind of be like when you go and pick strawberries or something. You're paying per pound, and you may or may not buy single pounds. So because we can buy partial pounds and then we will get partial pounds, this will be a continuous graph. So then, to actually graph it, we are going to have pounds of walnuts as our independent and our cost as our dependent. So if I'm graphing this, if I buy 0 pounds of walnuts, and we'll see, we'll count by 2s just so we said count by 2s and then I put a 3. 6, 8, 10, 12, 14, 16. So if I buy 0 pounds of walnuts, I pay $0. If I buy 1 pound of walnuts, I'm paying $6. If I buy 2 pounds of walnuts, I'm paying $12. And if I buy 3 pounds of walnuts, I'm paying $18. And because this is continuous, we're going to connect all of the dots. Okay? All right. So then, if it'll move, when technology does silly things. Let's see. Nope, it's just going to take it with it. Whatever. We'll see if it ever decides what to do. It did. So strange. Computers are weird. Okay, so a truck originally held 24 chairs. You remove 2 chairs at a time. The number of chairs n remaining after you make t trips is represented by n equals 24 minus t. So, starting with reasonable domain. I have a maximum number of chairs that I can have. And when I have that maximum number of chairs, I've made 0 trips. Okay? So then, because t is trips. So then, thinking about only having 24 and removing 2 at a time, that means the most number of trips I will have to take is 12 trips. So my domain is going to go from 0 to 12. Now, deciding if it's continuous or discrete, I can't remove half a chair. And as soon as I can't do a half of one of my variables, it is discrete because it's going to be individual dots because we cannot connect them. So then we have number of chairs as our dependent variable because the number of chairs depends on my number of trips. Okay, so 1 trip, 2 trip, 3 trip, 4 trip, sound like a Dr. Seuss book. But then number of chairs, I need to be able to go up to 24. So 2, 4, 6, 8, 10, 12, 14, 16, not enough. I'm going to have to count by 3s. So 3, 6, 9. Brain went dead for a second. 15, 18, 21, 24. Okay. So when I graph this, I start at 24. So I have to come up to this. And then I'm going down by 2 chairs every time. So 24, and I'm going to be ever so slightly off of mine. After 2 trips, I should have 20. It looks about right. And then 18 at 3 trips, and then 16 at 4 trips. And we already said it's discrete, so I'm not connecting the dots, but you can see the linear relationship that is happening. Okay, and eventually, way down here at 12, we would have 0 chairs. So that is why we have an end to our domain. Okay. All right, so then for number 8, we are determining if it is linear or nonlinear. So you just have to see if your rate of change is constant. To get from 2 to 6, that's plus 4. 6 to 12, that's plus 6. 12 to 72, plus 60. So as you can tell, not a constant rate of change. So this is nonlinear. And I'm going to abbreviate rate of change as ROC. So then with the next one, negative 2 to negative 9 is minus 7. Negative 9 to negative 16 is minus 7. And negative 16 to negative 23, also minus 7. So this one is linear because we have a constant rate of change. And if you can't identify that your constant rate of change is negative 7, then you need to make sure that you actually understand what rate of change is, because how quickly is it changing? So next, we determine if they are linear or nonlinear. With 10, we know this is linear because it is in slope-intercept form. So to graph it, we plot the y-intercept at 3, and then our slope is negative 6 over 7, so down 6, 1, 2, 3, 4, 5, 6, and over 7, 1, 2, 3, 4, 5, 6, 7. And then we connect the dots, like so. Perfect. So then this one, because we have this little squared here, we know it is nonlinear. So then you have to make a table of values. Remember, with your table of values, you should use negative 2, negative 1, 0, 1, and 2. So looking at this, if I plug in negative 2, I would have 4 times negative 2 squared plus 1. Well, 4 times negative 2 is 4 plus 1. 4 times 4 is 16 plus 1, so that's going to be at 17. And then you plug in the other numbers. Plug in, let me erase some of these numbers. We plug in negative 1. Negative 1 squared is positive 1. 4 times positive 1 is 4. 4 plus 1 is 5, so negative 1, 5. 1, 2, 3, 4, 5. Then we do it again. Notice I'm just erasing the numbers I wrote and putting in new ones. I plug in 0. 4 times 0 is 0. 0 plus 1 is 1. So 0, 1. Do it again. Come on. 1, 1. 1 squared is 1. 4 times 1 is 4. 4 plus 1 is 5. So 1, 5. And then 2. We have to put in 2. 2 squared is 4. 4 times 4 is 16. That gives me 17. So again, that's way up in the boonies. So my graph will look like a parabola. Okay. Last but not least, we got some funky stuff happening to the x, which tells us it is nonlinear. So again, when it's nonlinear, make a table. Negative 2, negative 1, 0, 1, 2. We have negative 3 times absolute value plus 5. So we have negative 3, absolute value of negative 2, which gives me a positive 2. Negative 3 times positive 2 is negative 6 plus 5, which gives me negative 6 plus 5 is negative 1. Right? Okay. So negative 2, negative 1. Got a point. Erase those numbers and put in different ones. Now we have negative 3 times the absolute value of negative 1. Absolute value is negative 1 is 1. Negative 3 times 1 is negative 3. And negative 3 plus 5 is positive 2. So then negative 1, positive 2. So then we get rid of those numbers. And we do it again. Absolute value of 0 is 0. Negative 3 times 0 is 0. And 0 plus 5 is 5. So 0, 5, 2, 4, 5. Get rid of those numbers. Put in the next one. Plug in 1. Absolute value of 1 is 1. Negative 3 times 1 is negative 3. Negative 3 plus 5 is 2. And some of you may be able to guess what our last number is. Boop. Plug in 2. Absolute value of 2 is 2. Negative 6 plus 5 is negative 1. And this one is absolute value, so it makes a V shape. Like this. And there you go. So then for 13 and 14, we want to identify our variables, write the function rule, and then answer the question. So with identifying these independent and dependent variables, and actually let's just pick another color and we'll just use all the colors. Why not? Sure. Okay, so 4A, our independent and dependent. We have the volume V remaining in a 243 cubic foot pile of gravel decreases by 0.2 cubic feet each shovelful of gravel spread in a walkway. How much is left in the pile after 25 shovelfuls? Man, that word is a mouthful. So my volume depends on my shovelfuls. So because of that, my independent variable is shovelful. And my dependent variable is volume. So then, to write a function rule for this, we're going to have volume equals, because remember, it's based off of those shovelfuls. We started with 243, so that would be like my y-intercept. My shovelfuls are like my x, and then I'm decreasing by 0.2, which tells me it's negative 0.2 s. And I kind of smushed that in there, so I'm going to rewrite it so that's a little bit prettier. 0.2 s. I feel like it still looks terrible. Okay, there we go, close enough. Probably looks worse. Anyways, overthinking too much. So, continuing on, we want to actually answer the question asked. So we want to know how much was left after 25 shovelfuls. So V equals negative 0.2 times 25 plus 243. And that, if you have a graphing calculator, you can pretty much just type straight in. Negative 0.2 times 25 plus 243 is 238 cubic feet. Okay. All right, so then we'll do the same for 14, starting with A. Your total cost, C, for hiring a garden designer is $200 for initial consultation plus $45 for each hour, H, the designer spends drawing plans. If the total cost is $335, how many hours did the garden designer work on the plans? So, starting with, and I'm going to move because lunch is starting soon, and people are going to try and come in. I don't want them to see me. Sorry, guys, if you were one of the people that tried to come in. But we get that because we are given letters for total cost an hour, that is your hint that those are your variables. So my total cost depends on the number of hours the designer spends drawing plans. So that means my independent variable is the number of hours drawing. Or you could just put number of hours each. And then my dependent variable is going to be my total cost, which is C. Goodness. So then, to get an actual function rule for this, I need to think about where did I start and where or how much does it change by. So because of that, and now there's extra voices in the background, hopefully, or hopefully not, but because of that, we are going to have beep boop. We have to start with our total cost because our cost depends on hours. The garden designer is $200 initially, so that is your y-intercept. And then your rate of change is your $45 per hour. So that means I would have 45 hours plus my $200 initial fee. Now, we want to know if my total cost is $335, how many hours did the designer work on the plans? Which is important because if you get charged $335, you want to know how long did that designer actually work. So, because we are given the total cost, we have 335 equals 45 times the number of hours that we don't know. I don't even know why I put a parenthesis, but plus 200, and now we're just solving. So we would subtract that $200 initial fee. Boop. 335 minus 200 is 135. And then we divide by 45. 135 divided by 45 is 3. So that designer took 3 hours to design your garden. Was it worth it? Was it not worth it? These are questions that you can actually do when you become an adult and have to do #adulting. Okay, so good there. So then for 15 and 18, let's see if it'll actually scroll. We need to determine whether the relation is a function and explain. So those directions should really be down here, but 'tis life. So when you are doing this, your x values cannot repeat. So I'm only going to write these reasons once so that I don't have to write it 1,000 times, but I don't know why it's not letting me scroll. It's just drawing. Dang it, computer. So function if no x values repeat. And you can use the vertical line test, which the vertical line test is a fancy way to say, can you draw a vertical line and it hit more than once? If it hits more than once, it's not a function. So if you notice with 15, if I were to draw a vertical line in here, I'm hitting 2 of my points, so it is not a function. Okay? And then with 16, if no matter how many vertical lines I draw, I'm only hitting it once, so this one is a function. And again, that reason that's above, it applies. There's no x values that are repeating. So then for 17, we have 2, 3, 4, 5, 6. No repeating x values. This is a function. For 18, we have -1, 9, 3, 5, 9. Uh-oh. We have 9 and 9. That's no good. No bueno. So this is not a function. Okay? So for 19 and 20, we have to use function notation, and we are just going to find f of 4. So because it's normally f of x, what this is saying is you are plugging in 4 for x. So f of 4 is -2 times 4 squared plus 3 times 4. F of 4 never changes. 4 squared is 16, so you have -2 times 16 plus 12. Keep in mind this squared only applies to what's right next to it. So then, -2 times 16 is -32 plus 12, and -32 plus 12 would be -20. Okay? So if I do f of 4 over here, it's going to look slightly different because it's a different equation. Oops, absolute value, not a parenthesis. I hate when the computer lags. There it goes. Okay. So then 4 minus 6 is -2, but it is inside of absolute values, which means it's going to be a +2. And then +2 plus 5 is 7. Now, although we have not explicitly said it, function notation, you can actually write your ordered pair for that point. So because I plugged in 4, my x value is 4, and -20 would be the y value. And over here, I'd have 4, and 7 would be the y value. So you can see how much different these graphs are to each other. So for 21, we need to find the range, and we are given the domain. So what it means is we are going to have to plug in all of these values in for x so we can figure out all the values for the range. So I'm just going to, over here, write range with the little squiggles because I know I'm going to need them. And I'm going to try and use colors as much as I can. So we will start with g of -3. We have -3 times -3 plus 4. -3 times -3 is +9, and +9 plus 4 is 13. So I know 13 is in my range. So then I do it again. G of -1.4. -3 times -1.4 plus 4. And to save some time, I am just going to type this into a calculator. So we have -3 times -1.4 gives us +4.2, and +4.2 plus 4 gives us 8.2. Okay, so then, changing up the colors, I'm going to plug in 0. g of 0 equals negative 3 times 0 plus 4. That gives me 0 plus 4, which is 4. And I just hate writing decimals, I guess. Sorry, guys. All right, so then last but not least, we plug in 8. G of 8 is negative 3 times 8 plus 4. Negative 3 times 8 is negative 24. And negative 24 plus 4 is negative 20. Okay? So all of my range values originate from plugging in my domain values. And technically, you should probably put them in numerical order from least to greatest, but honestly, I'll be fine with either. Okay, so then our last one, the Last Melon. If you can tell me what movie that is from, comment, because I will be so happy. But we have the function d of t equals 343t represents the distance d of t in meters that sound travels in t seconds. How far does sound travel in 8 seconds? So since t is my seconds, I'm going to plug in 8. d of 8 equals 343 times 8. And 343 times 8 is 2,744. And this is d of t in meters. So sound travels in 8 seconds, 2,744 meters, which I don't know a conversion rate, but I know it's a lot of distance. What's funny is I started writing meters and it didn't catch the M and the E. But that is the end of this review. If you still have questions, let me know. I don't know what that screen was about. That's so weird. But let me know if you have any questions. And good luck on your test. Don't forget to subscribe.